Okay, here's the first free response problem from the statics test. And we'll scroll along here so you can just find the parts you need help with. And then now I'm going to go through in some detail. So we saw problems like this in the unit. And so we have a ladder leaning against a wall. We're ignoring friction on the wall here, but there's definitely friction down here. This wouldn't work. And there's a person climbing up the ladder. Their center of mass is 1.2 meters from the bottom of the ladder. And the ladder is 3 meters long, and it's a 60 kilogram person. And the ladder is at a 30-degree angle here from the vertical. And so the first thing we want to do is a free body diagram. And so draw it as big as you can there. I didn't give you a whole lot of room for such a big one, but should be able to do it. And we have a normal force acting straight up and friction pushing in here down at the bottom. We have the weight of the person straight down, the weight of the ladder straight down, and then the force from the wall is really a normal force, but you want to name them differently, so I just called this the force from the wall. You could call this the normal force from the wall, or as long as you call them something different, because otherwise you might get confused later. And so that was worth 2 points, one for having all the x forces, one for having all the y forces. Didn't need to have the angles and stuff here, but that's going to be helpful later on. Now we want to figure out the force from the wall, and probably the best way to do that is sum the torques about this bottom point. And so we have a torque from the weights, and so if this angle is theta, then this is theta here too. And so you could, I don't know, make two parallel lines cut by a diagonal, so that's theta if that's theta. And so this has got to be 30 degrees. You could imagine making the ladder vertical, and so then the weights would line up with the ladder. So as you make this angle smaller, this angle would get smaller too. And we want the perpendicular components, so we want this side and this side for the weight, so it's opposite. So I have mg sine 30, then times the lever arm. mg sine 30 times the lever arm. Almost looks like I forgot the lever arm here and crammed it in there later. And so that happens to anybody. So whenever you write torque, check. Torque is force times the lever arm. Don't leave out the lever arms. That costs you a lot of points. And then the force from the wall. Different ways of, we want this component. And so different ways to get that. But this is 30 degrees here. That's theta. And so this is a right angle, so that's got to be 60. And the perpendicular component is the only part that has torque. And so that's opposite. And so we get a sine 60. And then this is in the opposite direction of the two weights. Weights are trying to rotate it counterclockwise, which I made positive. The wall force, this normal force, is trying to rotate clockwise. And so that would be negative. And then don't forget the lever arm, which is the whole length of the ladder. And that adds up to 0, and then if you're careful in your calculations, should be able to come up with 220.7. And notice that was worth 3 points, and so you got a point for the correct torque from the weights, correct torque from the wall, and then if you're able to correctly calculate, you got that point. And notice the +1 for a good try. If you showed you knew what you were doing but made some mistakes, you still got a point there, and it was earned. It was not a freebie. And now we want to, well, let's erase this stuff. And so now we want to determine the magnitude and direction of the force of the ground on the ladder. So that sounds kind of strange. Force of the ground, what do they mean? Well, we had a homework problem like this. There's a ladder. You could think of these two forces on the ground, the normal force and the static friction, as components of the ground force. And so that is a perfectly fine way to consider it. And so I need to figure out what those two are. So I sum the forces in the x, set it equal to 0, and I find out the static friction equals the force from the wall, which I have from above. So static friction is 220.7. And again, that's only if it's just about to slip. And so static friction only is as big as it needs to be. And so well, it's not equal to mu n is what I'm trying to say here. Not equal to mu static times the normal force. We could solve for the minimum coefficient of friction to keep it from slipping. It gives us this force, but static friction is as big as it needs to be, 220.7. And then some of the forces in the y equals 0, and so the normal force was up, two weights are down, and it's just equal to 882 newtons. And then to get the magnitude, I square both those, add them, take the square roots, and then inverse tangent of the y over the x, and I get negative 75.95, and so that's 104 degrees. You had to be clear about what you meant by your direction. And so if you go and look, if you're just using a normal coordinate system, then the direction of the ground force is in the second quadrant here, it's somewhere here. And so you had to somehow indicate you knew that, because I do want the direction, just not just a number. And if the person climbed higher in the ladder, how would that affect the normal force of the ground on the ladder? It's going to stay the same. Some of the forces in the y are what dictate what the normal force is. Nothing's going to change here. And so as they climb up, nothing would change as far as the normal force. Other things would change, though. The person is going to be applying more torque, and because their lever arm is getting longer, and that's going to change the wall force and friction, but it's not going to change the normal force. Okay, let's take a look at the next one in the next video.